This is how most of computer science texts define asymptotic notations. While being formally correct, they are a mouthful to digest, to say the least. Instead, I'm going to show you 3 basic rules. In using these rules, you will be able to define these notations on your own. Let's get started. The first rule of the game is that we want to make estimates about the runtime of an algorithm in terms of bounds. Big O is an upper bound or an overestimate. Your runtime will always be less than this estimate. Big omega is similarly a lower bound or an underestimate. And your runtime, TFN, will always be greater than this estimate. Big theta is simultaneously an upper bound and a lower bound. One thing to note here is the variable of runtime and upper and lower bounds. Usually denoted by n, this is the size of input to your algorithm. The size of input to a sorting algorithm is the size of that list. Almost any algorithm that takes a string as input has the number of letters in the string as its input size. This algorithm checks whether an integer is prime or not. The size of input is the number of bits required to represent this number, which is log p in this case. Similarly, following mystery algorithm also has log p as input size. Okay, so we are interested in upper and lower bounds as a function of the size of the input. The second rule says that we don't care how an algorithm performs on small inputs. Whenever someone gives us a bound on runtime, we only need to make sure that the bound is valid for really large n. How large is really large, you ask? Well, as large as you want. When you prove such a bound, you have the liberty to specify a minimum input size, n0. And as I said, n0 can be as big as you like. This may sound weird at first, but the idea is that small inputs can't be the representative of an algorithm performance. For example, look at this graph of x plus 1. This completely dominates the log x. Let me give log x a push by multiplying it with 50. Now the blue curve of log x seems to be above x plus 1. But wait, its glory is short-lived, and after around x equals to 100, x plus 1 dominates again. Let me give it a real boost by multiplying it with 50,000 and also taking the power of 3 of the log. Whoa, the purple seems to grow as fast as the vertical line, much faster than x plus 1. Let's zoom out and see what happens in the far, far future. Still nothing. Whoa, something happens at around 2 million, I think, and reign of purple is over. Let's zoom out more. X plus 1 is so dominant in the far future that it doesn't look like purple curve even had a chance. The purple seems as beaten up as the horizontal line, as if both of these log terms were equal to 0 compared to x plus 1. This is the reason that we only care about really large n. For a clearer picture, when n is small, there is too much noise. The real picture becomes visible for really large n. So the rule 2 says that T of n should be less than or equal to f of n for only n which are larger than n0. And you can choose n0 to be as big as you want. Rule 3 says that the constant in the coefficient of a function doesn't matter. So if t of n is upper bounded by f of m, then 2 times t of n should also be upper bounded by the same function. Even 100 times t of n, which is equivalent to calling the same function 100 times, should be upper bounded by the same function. Not just 100, you can pick any constant you want, and if you multiply it with t of n, it should still be upper bounded by f of n. And this is achieved by allowing a constant to be multiplied with f of n when trying to upper bound t of n. So we want t of n to be less than a constant c times f of n for any fixed choice of a constant c. That's it. Based on these 3 rules, we have defined that t of n is big O of f of n whenever we can find a constant so that t of n becomes less than or equal to c times f of n for really large values of n. To be precise, if you need to prove an upper bound, all you need to do is find 2 constants, c and n0, so that t of n is less than or equal to c times f of n whenever n is bigger than n0. For example, if you want to show that 3n cubed plus 2n plus 7 is big O of n cubed, the step 1 is to write down what we need to do. We need to find 2 constants so that this becomes true. Here is a trick to finding these constants that I use, and it works in about 90% of the cases. I set n0 to 1, and I set c to the sum of all the constants in the equation. This does not work always though, okay? So in this case, we'll set n0 to 1 and c to 12. Start with left hand side. Since n is at least 1, I can multiply n and only get larger value. And that gives me 12n cubed. So I'm done. Let's try this uglier but more general term. If we prove this, we will always know how to upper bound a polynomial. We have d plus 1 terms on the left. Let's try n0 equals 1 and try to figure out c by algebra. Again, I change n to the d minus 1 to n to the d, n to the d minus 2 to n to the d, and other terms to n to the d as well. I can do that because n is at least 1, right? If I take n to the d common, I get a value of c, which is the sum of all the coefficients in the original polynomial. So we have proved that to find a big O upper bound of a polynomial, we just take the largest or the fastest growing n term without its coefficient. The upper bound for this term is n to the 4. This term is upper bounded by n cubed. But you can also say that this term is upper bounded by n to the 4 because n cubed is upper bounded by n to the 4. How about this one? The fastest growing term here is n square log n. So it's big O of n square log n. This is big O of the fastest growing n factorial term. The fastest growing thing in this expression is a constant. So we write this as big O of 1. This is big O of 1 over n, although you may never encounter this in algorithms, because each algorithm takes at least a constant time. Let me just provide you with a non-exhaustive list of functions that we use in asymptotic notations. A constant is a slowest growing expression for algorithms, so any algorithm that takes constant time is the fastest possible algorithm. There is something called log star. It grows extremely slow, but it's faster than any constant. Log n grows faster than log star. Log n grows faster than log n. Any positive power larger than 1 of a function grows faster than that function. So log squared n is greater than log n. Any power of log is going to be slower than any power of n, where both powers are at least positive. As big O is an upper bound on runtime, big omega is a lower bound, and is identically defined using the same three rules. So T of n is big omega of f of n whenever T of n is greater than or constant times f of n, where n is at least n0. The only change is in the direction of the inequality. In the big O case, we want to make this right side big to make our life easier. So we choose a C which is really big. In the big omega case, we want this side to be smaller. So we choose a C which is really, really small. And finally, T of n is big theta of f of n if you can find constants n0 and c, so that T of n is less than or equal to c times f of n, and T of n is greater than or equal to f of n over c. Learning asymptotic notations is a bit tough task, and I hope that I have eased your pain somewhat. Happy thinking!